So next I will talk about variable type analysis, which, like the name suggests, is looking at variables and also at assignments to variables. Let's take a look at a concrete example. So here we're having an example program that is actually having these procedure calls here. So we're first instantiating an X object, okay, and then this is being assigned to A, and then A is being assigned to B, and B is being passed as a parameter here, okay, as a parameter to a call O.F. So this call here can actually be a polymorphic method call in itself, right? And that means it can actually go to this particular implementation of F here, but it can also go to this particular implementation of F there. And so this means that this X object may actually end up being assigned to this C parameter, but also to this one down here. Okay, and the idea is that we want to be able to resolve these kinds of assignments so that we know that this call to M at this point can actually go to X.M and this one here as well. Okay, and the idea is that we do this through a so-called type propagation graph. So we will be building up a graph that, for instance, keeps track of the fact that the type X was being assigned to a variable A here, right? So this is this initial assignment here. So we have an object of type X, which is associated with this variable node A. And then we have edges in this type propagation graph here that represent all the possible assignments that you can have in your program. And again, this is a flow insensitive representation. So we don't know in which order these assignments happen, but we know that they happen at some point in time. And so, for instance, here we are assigning A to B, which is why we have an edge from A to B. And then B can be assigned to this formal parameter C in the method A.F, which is this node, or it can be assigned to C in the method B.F, which is this node, okay? And so the idea is that you scan through your program. For each assignment, you add such an edge to the graph, and then you do a type propagation. So for every assignment of a new object that you have here, you have such an initial type assignment to that node where the initial assignment happens. And then this is being propagated through this graph only. So you're taking this set X and you're propagating it along all the edges until you can't propagate it any further. And then you have your final type propagation graph. And now you can simply read off the results. So you now know that you can have the type X for A.F.C, and therefore this call can actually go to X.M. Okay. What you will notice here is that in order to be able to build this graph, you already need to know something about your call graph, right? So I have an edge here from B to A.F.C, so I already need to know ahead of time that this call from F can actually go to this particular instance of F here, and maybe also that one here, right? So it's a bit of a chicken egg problem, right? So we want to construct a better call graph, and we also want to do some assignment analysis, let's say, right? But in order to do that, we need to have a call graph in the first place. And so the idea is that you first form an initial conservative call graph, which is usually done using CHA or RTA. So you do that up front. You can even do that using VTA in the next step. So basically you can construct a call graph, let's say, using CHA. You can then do VTA on top of that, which gives you a better call graph. And then, as it turns out, you can use that call graph again and do another run of VTA on top of that, so a second time. And that then has the potential to actually prune down the call edges further because you basically have a more precise call graph to begin with. Then once you have your call graph, like I said, you build this type propagation graph. Then we're actually also collapsing strongly connected components. I'll still be showing you an example of this. And then you're propagating types in a single iteration. So that actually makes VTA also relatively fast. When you build this type propagation graph, there are a few special cases. So I've shown you this very simple case where you have, let's say, a parameter A and B in a procedure C.M, right? Then you, if you have such an assignment here, you will have an edge from B to A, right? Because B is assigned to A. But in VTA, you will have the same edge also in the case where B is actually an array access, like here. So as you notice, here we are not actually copying the entire array to A, but only a single element. But that is being abstracted by that particular edge, right? So here, this is basically being conflated. So that's a deliberate choice to make the analysis less precise than possible at this point. Similarly here, if you assign to an array, you will also see such an edge. So it's just a design choice. Also, what's important is if we assume that F is a field declared in a type A, so that means A, so small a here is actually of type large A, then we will see an assignment edge from this value here, so from B, not to little a dot f, but to large a dot f, right? So the assignment goes to the type or the field, annotated to the type, and not the actual variable that's holding it. And this is called a so-called field-based analysis. So we are ignoring the concrete variable. We are only looking at the type that this variable has. That's another deliberate abstraction that is being chosen here, just to make the analysis more simple. And you can see it as a form of widening, basically, right? So we are choosing a more coarse-grained abstraction in both of these cases to make the analysis more tractable. Let's take a look at a more concrete example to run you through this. So let's assume we have the following type hierarchy. So C is a subtype of B, and that's a subtype of A. And now we're actually having some variables declared of these types, and they are being initialized, and then they're also being assigned to one another. Then this will give you such a graph here. And why is that? Let's take a look at that. So for instance, we have this assignment from A2 to A1, which gives us this assignment edge here. We have one from A3 to A1, which, from A1 to A3, which gives us this edge here, and so on. Okay, I guess that's very simple. You get the gist. And now, once we have built up that initial graph, we still need to initialize it with the types that are instantiated here, and then we need to do the propagation, right? So let's take a look at the instantiations again. You will see that A1 is being initialized with type A, so that's why we have this set with only A in here, right? Because A is the only type that is ever being directly assigned to A1. And we do the same also for the other variants here. And then we simply, once we have done that for all the different variables, right, then we simply do the next step. So in the second step, we identify so-called strongly connected components. So a strongly connected component, or SCC, is one where every node is reachable from every other node, right? So this, for instance, is an SCC because A3 can be reached from all the other nodes in the same SCC, and the same is true for B3. And such nodes here, if you take a look at them, or such components, we can treat them as a single node. Why is that? Because we know that once we propagate any type into this node, by definition of the SCC, it's going to reach all the other nodes in the SCC as well, right? So that means within an SCC, every node is equal, and therefore we can just treat them as one. And if we do that, that actually speeds up the algorithm, right? So basically, these nodes are being collapsed into single nodes, And then we simply, in the last step, do the type propagation. So this means in this case, we will propagate, for instance, A from here to there, which is already there. Then we'll propagate it over here. We will also propagate B to this node B1, but we will also be propagating C to this node B1, which means it's being added to the set as well. And then we are done. We have reached a fixed point, and that's then also our final result. So now we know that B1 might point to objects of type B and C, for instance, or A3 might only point to objects of type A. So the good thing is that this is also more precise than RTA because it considers only those types that actually have a chance of reaching the particular call site in question, right? So it's really looking at these assignments, and of course they matter, right? Because they determine which objects flow where in your program. On the other hand, it's still relatively fast, right? So it treats the same all allocation sites that share the same type. So if you, let's take a look at this program again, right? So here we had different allocations of the same type, right? So here we are instantiating an object of type A, and here we're instantiating another object of type A, but both are being represented by the same type identifier A, right? So we don't distinguish this allocation from that one. We don't even want to know that this is a different object from that one. It doesn't matter for us, right? So here they're being combined into a single representation, and that makes it relatively fast, but also still relatively precise. Drawbacks, it requires an initial call graph, like I discussed. So actually you could say it's a refinement algorithm because you take the initial call graph and you refine it using VTA. And also still some imprecision remains, for instance, because VTA models fields of different objects as a single node. I just told you it's a field-based analysis, right? And in the end, we will be talking about another pointer analysis that is actually distinguishing these fields from one another, and that can sometimes increase precision, at least by a little bit. So just as a little excursion here, if you have these different kinds of field representations, there are actually different types that you can distinguish. So if you have a field access such as A.F, it can be represented in 3 different ways. So you can have a so-called field-sensitive representation that is representing A.F just by itself, right? So we are talking about the concrete variable that is actually holding the concrete object that is whose field F is being accessed. And this is the most precise representation you can think of. But then there's also a field insensitive analysis, which is one field insensitive representation, which is one where you forget about the field access itself. So here the access is being represented by A dot star, or sometimes also just A. So basically saying we know we have accessed the field of A, but we don't really care about which one. Okay. So you're basically representing the field by its owner object. And then there are these field-based representations that I talked about where A is the class or type of small a, right? And we are using that as a representation. And in VTA, we have a field-based representation. And in a regular points to analysis, which is also often called Anderson style points to analysis, and that I will still be covering in a few minutes, we are typically using a field-sensitive representation. Then the next kind of analysis I want to talk about is DTA. And this is a bit like the smaller brother of VTA, because DTA is actually not more elaborate and not more precise than VTA, but actually the other way around. So DTA actually abstracts a bit more of what you have seen in VTA, and therefore gives you a more coarse grain and also more imprecise representation, but it can be computed more quickly than VTA, so it may sometimes still be useful. So in order to understand how DTA works, let's take a look at the same example that we had earlier. So this is still the same code, but now you see that we are looking at a much different graph, right? So it's a lot smaller than we had than the one we had earlier. And in particular, what you can see is also that the graph is labeled differently, right? So previously we had variable names as nodes here, and now we actually have type names. And what's important to understand, and that's already here in the name, these are not runtime types of objects that are instantiated, but actually these are declared types. So these type identifiers here, they come from these type declarations up here. They do not come from these instantiations that you have here. Okay, so this label comes from here, for instance, right? So that's an important distinction. So we have types and not variables, and they're actually declared types. Okay. Now let's take a look at where these edges come from. So down here, for instance, we are assigning a variable b3, which has a declared type b, to a variable a3, which has a declared type a. Okay. And here we did not look at instantiations, right? We were only looking at the declared types. But because of this assignment, we have an edge from B to A, okay? So we just encode that there is some variable of declared type B being assigned some other variable of type A. And we do that for all the assignments, right? So we have another one here that gives us this edge. We have another one there that gives us this edge, okay? And the rest is exactly the same. So again, we have these sets being annotated here for the allocation sites. And here, for these annotations now, we do look at the allocations, of course, right? So here we have this runtime type A being assigned to a variable of declared type A, which is why this A here is associated with this A node, okay? And the same, in this case, coincidentally, we have B being assigned to B and C being assigned to C. And that's our initial type assignment. Again, we detect and merge these strongly connected components, and then we propagate the type information. And this gives us our final solution, which in this case you see here. So the good thing is this is faster than VTA, so the graph is smaller like you saw. It can be a lot smaller actually, because obviously there are much fewer types than variables in most programs. And the propagation therefore can also be faster. It's also more precise still than RTA, right? Because it is looking to assignments to some extent, just not at assignments to individual variables, but between types. Because of that, it's a little less precise than VTA, right? And how much that matters depends a bit on the programs you're analyzing. So the key difference is that it does not distinguish variables of the same type, whereas VTA does. And you can also see one-to-one correspondence if you look at the different graphs, right? So this is the graph we had actually computed for VTA. This is the graph we had computed for DTA. And if I turn this around, you will actually see this one-to-one correspondence, right? So basically you have this node here that represents all of what's happening up here. You have this node here that represents all of these variables. And this one here is this one. And then, this is basically being, in the end, represented by this one strongly connected component, because this merges all of what's happening here, because all of these variables have the same type, the same declared type, and all of these have the same declared type as well. That's how you can see that this is basically a abstraction, a direct abstraction of this one here. Okay. Then in the next and final episode of this week's lecture, I will be talking about Spark, which is a general framework for call graph construction and also pointer analysis, which is implemented in Suite. And like I said, you also have a similar kind of support in Kesa through the LLVM framework. And most other program analysis frameworks will have some variant of this one way or the other, because call graph construction is always important. Although I have to say that Spark is actually relatively versatile and powerful. So it's, yeah, I haven't seen many implementations that actually implement so many different call graph construction algorithms. Sorry. There's one other framework which is called DOOP, which actually specializes on pointer analysis in particular. That probably has very similar support, and in some cases even goes beyond that. So if you are really interested in learning more about pointer analysis, I recommend you also take a look at the DOOP framework as well. Yeah, so we'll be talking about this after the next break. I'll see you then.